The following is the video solution from JSDT Solutions. Question 9.1 says, in the diagram, O is the center of the circle, and then we have OD bisects the chord AB. Now we have to prove the theorem, which states that the line from the center of the circle that bisects a chord is perpendicular to the chord. So that is that OD is perpendicular to AB. Okay, so this is really just the converse of that first theorem that you learn. To prove that these two are perpendicular, it's going to be very similar to the way we prove that the line from the center of the circle perpendicular to the chord bisects the chord. So we're going to start with constructions. We're going to construct a line from O to A and then a line from O to B. And then we need to write down any constructions made. Okay, and then after we have done that, we can focus on this. We can prove that these two triangles are exactly the same. In other words, that they are congruent. Because if they're congruent, then it means that all their corresponding sides and angles will be equal. Emphasis on the angles. So it would mean that this angle is equal to this angle, and this angle is equal to this angle. And then these two angles would be equal. And then when we get to this point, we'll be able to show them that each angle is 90 degrees. Okay, so let's go ahead and start proving. So let's introduce the triangles. We're introducing the triangles AOD and BOD. So in triangle AOD and BOD. And we can focus on the sides that are equal because we don't really have any angles that we can prove are equal. So first notice that OA is from the center to the circumference, and so is OB. So they're both radii. So we can say that OA equals OB, and the reason for that is radii. Okay, they are radiuses of the circle. Then we have OD, which is a shared side. So of course it's going to be equal to OD in the other triangle, and we can say shared side. And then we have one more side that is equal. They already told us that AD and BD were equal, so we can tell them that AD is equal to BD, and this is because it was given, so it's given. Okay, it's a given side. So this concludes that triangle AOD is indeed congruent to triangle BOD because we have three sets of equal sides. Three corresponding sides are equal in each triangle. Now, what that concludes is, because these two are congruent, it would also conclude that these two angles, this angle is equal to this angle. So let's just put it like that. But we'll call it ODA or ADO, that's fine, and BDO. So we're saying that those two are equal. So angle ADO equals BDO, and the reason for that is because we had congruent triangles that we proved. Now, they are equal, but that doesn't already conclude that they're equal to 90 degrees each. How we can prove that they're equal to 90 degrees is that they lie on a straight line. So these are exactly the same angles. What if they were called X, right? If you add these two and they have to add up to 180 degrees because they lie on a straight line, then this has to be 90 degrees and that has to be 90 degrees for them to be equal. Okay, so that is the idea behind it. So we can tell them that ADO, angle ADO, plus angle BDO, that they add up to 180 degrees because they are angles on a straight line. Okay, and because we know that they're exactly the same, look at what we can do. We can update this equation. So we can go ADO plus, and then in place of BDO, we can replace that with ADO since they're exactly the same. It's equal to 180 degrees. And then this makes up 2ADO, which is equal to 180 degrees. And if we divide both hand sides by 2, then finally angle ADO is equal to 90 degrees. And since that's equal to 90 degrees, then BDO is also equal to 90 degrees. So they're both equal to 90 degrees. And if they're both equal to 90 degrees, then that would conclude that line OD really is perpendicular to AB. So there's our conclusion. So therefore, OD is perpendicular to AB. And that is how we prove that theorem. Question 9.2 says, in the diagram, E, B, F, S, and P are points on the circle centered at O. GB is a tangent to the circle at B. And then we have that FE is produced to meet the tangent at G. And then OT is drawn such that T is the midpoint of EF. GO and BO are drawn, and BS is drawn through T. And lastly, we're told that PS is parallel to GF. So the first question, 9.2.1 says, prove given reasons that OTBG is a cyclic quadrilateral. So let's see what they are referring to. OTGB is this over here. So we have to prove that this is a cyclic quadrilateral. Okay, so it would mean that it would be within its own circle. There are three theorems that we can use to prove that a shape is a cyclic quadrilateral. The first theorem is if we have some sort of quad in a circle, and you notice that the exterior angle of this quad is equal to the opposite interior angle, then it means that this is a cyclic quad. The second way to prove that a shape is a cyclic quad is if we have a quad inside a circle, and you notice that the opposite angles of these quads add up to 180 degrees, then this is a cyclic quad. And then the third way to prove that a shape is a cyclic quad is if you have this situation where you could have a chord or an arc and you notice that there are angles at the circumference. At those angles are equal. Then this is a cyclic quad. So based on the diagram that we have to look at what would best suit these scenarios. Now, already looking at this, I see that it has lines going across. So let's try to see if it is this situation over here. Okay, so looking at this and looking at what we know about the angles at the circumference. So you can look at it in different directions. You can look at maybe this angle is equal to, and let's use a different color. Maybe this angle is equal to this angle. But for now, I don't really see these angles traveling anywhere. So then we could look at it as maybe this angle over here is equal to this angle. This one is specifically at the center, but I can't seem to move that one either. So we could also just focus on these two angles. And let's just see, based on where they are, this one is between a tangent. And do you see that they said that OT was drawn such that T is the midpoint of EF, okay? So if T is the midpoint, and I'm going to have to remove this because it's going to just distract. If T is the midpoint of EF, then we can see that the previous theorem we just worked on, that proof, is showing up here. We have a line from the center of the circle to the midpoint of a chord, okay? And that line would be perpendicular to the chord. So that is 90 degrees over there. Now, if this is 90 degrees and we're trying to show them that the angles in the same segment are equal, then this should be 90 degrees. Can we see how that is 90 degrees? Well, yes, because this from O to B is a radius, okay? That is the radius, and this is a tangent. The angle between a tangent and a radius is 90 degrees, okay? The tangent is always perpendicular to the radius at the point of contact. So we can see that this is the angles in the same segments that we have over here. See, those two lines cross like that, and so that angle is equal to this angle. Okay, so let's go ahead and find those individually. We're going to tell them that OTG is equal to 90 degrees. And that is because of the line from the center to the midpoint of the chord. And then we also know that OBG is also 90 degrees. And that's because the tangent and the radius are always perpendicular at the point of contact. So OBG is also equal to 90 degrees because of tangent perpendicular to radius. And so we can conclude that these two are equal. So that concludes that OTG is therefore equal to angle OBG. And so that would prove that that is a cyclic quad because we had angles in the same segment that were equal. So OTBG is a cyclic quad. And the reason we can actually give is it's the converse of that theorem. So we'll tell them it's the converse of angles in the same segment. Okay, And remember, it is the converse because they didn't tell us that this was a cyclic chord. We had to prove to them that it's a cyclic chord. So because the angles in the same segment are equal, it is therefore a cyclic chord. Okay, and that is our answer. Moving on to the next question. Question 9.2.2 says that we have to prove that GOB is equal to S, angle S. Okay, so let's look at this. GOB is over here. So remember, everything we're doing now is with the knowledge that this shape is a cyclic chord now. So this is GOB, and we have to prove that it is equal to angle S. Okay, so how do we get from this point to this point? Well, this is a cyclic chord. So you see how these lines go across again? We can show them that GOB, this angle over here, is actually equal to, and you see that the lines go across like that, okay? So it would mean that the chord supporting this angle, that it is on the circumference of whatever circle it belongs to, okay? If there was a circle over there, then that actually proves that angle GOB is equal to this angle over here, which is angle, we can call it GTB or BTG. Okay, so those two would be equal. And then remember that we have parallel lines. So these two lines, if they are parallel, it means that we have corresponding angles. So that angle is actually equal to angle S. And that is why GOB would be equal to angle S. Okay, so let's just go GOB. We can start off there and say that angle GOB is equal to that angle over there, which is angle GTB. We can just call it GTB, that's fine. And the reason they are equal is because they are angles in the same segment, since there is a circle there and that shape is a cyclic chord. Okay, and then the angle GTB is equal to angle S because we have corresponding angles. It's an upside down F because of those parallel lines. Okay, and then we'll tell them corresponding angles and make sure to point out the lines that are parallel. Okay, because PS is parallel to GF as they said, and that would conclude, since they're both equal to angle GTB, that angle GOB is finally equal to angle S. And that is our answer.